Hi, my name's Hannah and I'm a third year aeronautical engineering student at the School of Engineering here at UNSW Canberra. You've probably seen on YouTube videos of people slamming two steel spheres together like this, and when you put paper at the collision point, it burns a hole in the paper. And my project has been focusing on trying to explain why this happens. Apart from the videos that you can find on YouTube, there's also one piece of literature that states that this experiment will only be successful with 2-inched chrome steel spheres, and we've managed to prove that this is actually incorrect. We hypothesised that spheres of different materials other than chrome steel and different diameters other than 2 inches would also be able to produce this effect. And we hypothesised that it depends on the resilience of the material as to whether it worked or not. The resilience being how much energy a material can absorb without plastically deforming. Unlike in the YouTube videos, we wanted to conduct a systematic investigation of the process. So in order to do this, instead of just doing this with the spheres, we wanted to be able to measure the kinetic energy on impact, so we built a drop test rig. One of the first tests that we run was to find out the minimum kinetic energy on impact that each of the size spheres had that would still burn a hole in the paper. And what was interesting was that the small spheres required less kinetic energy to actually burn a hole in the paper. Through the use of high-speed imaging and Hertz's contact theory, we could film the collisions of the spheres, which allowed us to find the contact areas of the spheres. And the reason the small spheres required less kinetic energy to burn a hole in the paper is because they had smaller contact areas, which meant for a smaller kinetic energy, they could produce the same pressure reading as the bigger spheres with a bigger kinetic energy. To investigate whether a shock was generated, we needed an imaging system that can detect density changes in a transparent fluid. And for this, we used a very sensitive schlieren imaging system, and a video explaining how this works is linked below. In lots of the YouTube videos that I spoke about before, they say that on collision, a shockwave is produced, but we believe this isn't true because lots of the features you would expect to see with a shockwave aren't actually visible in our tests. For example, a shockwave would have a distinguished front coming from the collision site, and it would rebound off any solid objects such as our pressure transducer, but you don't see that happening. Our pressure transducer also shows a drop in pressure, which is what you would see with an expansion. If it was a shockwave, it would be an increase in pressure, but that is not the case.
Hi, it's Future Hannah here, and since we've recorded what you've just seen, we've verified that there really is no shock with experiments involving spheres and nothing else at the collision site. However, if we put a combustible material at the collision site, it may produce a shock, and we can prove this both through our schlieren imaging and through our pressure measurements.
From the tests we've conducted, there's evidence to show that materials other than chrome steel, such as glass, actually do work, and sizes other than 2-inch steel spheres also work, such as this 25mm sphere. But materials with resilience values that are different to glass and steel, such as phenolic resin, don't work. I'd like to say a big thank you to my lecturer Harold Kleiner and the university's professional staff, especially Brendan Wallace, in helping me conduct this research. Brendan actually designed and built the whole test rig, and I wouldn't have been able to use any of the schlieren equipment without the help of my lecturer Harold.